All right, we'll get started. So, so we are continuing our discussion of surface integrals today. So just to recall what the basic gist behind surface integrals is, maybe I should start here actually. So we saw last time if you have that S is some kind of surface. So if S is a surface, that's parameterized by some function R of U and V, then the flux of your vector field F across S is given by the double integral over S of F dot ds. That's what we call this thing. That's what the flux is. And to calculate it, you're going to take the double integral over the domain of the parameterization of F of R of UV dot RU times R V dA. Now, we notice here that if S is a graph that's given by the function z equals gxy for some xy that's in D and that has upward orientation, then there are a couple shortcuts ish. Basically, it turns out that in that instance, you have that, this comes from the fact that in this instance, you have that Rxy, so Rx times Ry, or which, flipping U and V to X and Y because we can. That's just going to be negative Gxi minus Gy, minus Gyj plus K, which is written in the bottom paragraph here. So that's the case with upwards orientation. So that's what we looked at last time. Okay, now of course, z doesn't have to be a function of x and y. You could also have that say x is a function of y and z, or y is a function of x and z. And the principle is pretty much the exact same thing. If you have that y is a function of x and z, then you have that your parameterization is negative gx1 negative gz in that case for the necessary cross product. And if you have that S is given by x equals gyz, then again it's the same basic idea: 1 negative gy negative gz for this instance. So it's the same basic idea that we saw before, just with with different variables as need be. So let's look at this example. Suppose we've got the flux of F. F is given by x 2y 3z. It's a linear vector field. It's going across this cube with these vertices with outward orientation. So even if you can't draw it, even if you can't draw what the picture is, we should have an idea about what this thing actually looks like. We have here a cube. Right? So I'm going to draw a rough idea of a cube. So it's a cube here. Maybe this is the cube x, the side x equals 1, z equals 1, and y equals 1. On the opposite side, we have the same exact phenomenon. And through this cube, we've got our axes. So again, this is a bit of a rough picture, but just to give you an idea about what this thing looks like. We should always try to make an effort to kind of visualize our scenario, even if we can't get a great idea of what it looks like. We should always make an effort. We want to know about the flux of this vector field across this cube. Well, one little obstacle here is that this cube has 6 faces, which means we're going to have to do 6 different integrals, which might sound kind of cruddy, but it turns out that these surfaces are very easy to work with because they're graphs of constants. So basically, we need to do 6 different integrals. we need to do 6 different integrals, basically. One for each face. So let's start off with z equals 1. For z equals 1, we know that the surface is the graph, and the surface is going to be the graph of the function z equals 1. So using our little trick, we have that ds is just going to be, in this case, gx and gy are both 0. So this is going to be 0, 0, 1 dA, or in other words, k dA. And also, we also know that on this surface, we've got f of r of x and y. Just plug in x, y, and z equals 1 into the graph, we get x, 2y, and 3, because z is 1. So what that gives us is that the dot product, the dot product f of r of x and y dotted with rx cross ry is going to be x, 2y, 3 dotted with 0, 0, 1, or in other words, just 3. So the double integral over this first surface, which I'm going to call S1, the double integral over the surface S1 of f dot ds, well, that's the double integral over the domain of the parameterization, which is just the unit square, or not the unit square, but the square from -1 to 1, from -1 to 1, of 3 dA, or in other words, 3 times the area of D. The area of the D is 2, so that top integral is going to be 6. Easy enough. And meanwhile, for z equals -1, it's almost the same story, only in this case you have g xy is the constant function -1, and f of r of xy is x, 2y, -3, and accordingly rx cross ry is actually equal to negative k d, negative k in this case. But you maybe can see this already. I'm going to call that S2. Maybe you can see this already. That means that this second double integral, it's going to be the exact same thing as before, right? In this case, it's going to be x, 2y, -3 dotted with negative k dA, or in other words, once again, double integral over d of 3 dA, which is no more, no less than 6, as before. So all we've done so far is find what the flux is across the top and bottom face of this thing. So we're going to have to figure out what the rest of it is, which I'll do really quickly. Let me just erase some stuff. So for the, I'm going to call the y faces, or actually I'll do, I'll do the y faces. No, I'll do the x faces. So I'll call this one is going to be S3, and back here is going to be S4. So it's pretty much the exact same story. So for x equals 1, it's going to be very similar. In this case, you have that x is some function of y and z, which again is just the constant function 1. So we have that ry cross rz, the what we're really interested in this case, is going to be is going to just be 1, 0, 0. By the way, for those of you who are paying very close attention, you'll remember that this ry cross rz represents the unit normal vector. So yeah, of course it's going to be 1, 0, 0. That's going to be orthogonal at that point. That shouldn't be surprising at all. All right, that's just I. Same thing as before. And we saw that with the normal vector for the top and for the bottom. So maybe we can see where the story is going at this point, but we'll look at that in more detail in a little bit. So we know this, and we also know that f of r, y, z is going to be 1, 2y, 3z. So the dot product is f of f of r, y, z dotted with ry cross rz, which is just going to be 1. Same as before, only with 1 instead of 3. So it's the same exact idea where you have that the double integral over S4 in this case, f dot, oh, no, not S4, S3. I called that S3. It ends up not mattering, but I'll be consistent. F dot ds, that's the double integral over d of just the function 1 dA, or in other words, the area of d, which is 1. I'm trying to make it a little more obvious that it's actually equal to 1. And for x equals -1, it's the exact same idea, right? Because in this case, we have that ry cross rz is going to be negative I, since in this case we have, we're going to have that gyz is constantly -1. So it's the same idea in this case. And now that we know that, now that we have that principle, we can say in this case that, actually, strictly speaking, this should be the other way around. Not negative I, not ry cross rz, but rz cross ry, because it's negatively oriented, because it's oriented backwards. Sorry, I got that backwards. So let me fix that real quick. Since it has to be backward oriented. Because we're talking about the outward flux. So the double integral over S4 of f dot ds is the double integral over d of, now f of r of zy in this case is going to be -1, 2y, 3z, dotted with -I dA, which again is just going to be the double integral over d of the constant function 1, which is just, oh, sorry, I said 1, but I meant 2. I said 1 in the first place, but I meant 2, because that thing is actually going to be, going to have, rats. I screwed something up. Okay, it's not a bad screw up. I'm just realizing that I made a mistake. The area is 4, not 2. The side edges are 2, but the area itself is therefore going to be 4. Silly me. That's, I worked too quickly there on that one. So we'll fix that in the actual notes when I post them to Canvas. So that should be should have been 12, not 6. Unfortunately, I can't turn time back, but I'll make sure I keep that in mind when I deliver the final answer. Sorry for the confusion. So let me just conclude this. I need to erase some stuff again. 1 second. So that just leaves what I'm calling S5 And back here is going to be S6, which is for y equals 1. And keeping in mind the correction I had to make last time. So we have that, in this case, we're looking at the that ds being, in this case, negative gx 1 gz, where gxz is just the constant function 1 again. But that's just going to be j dA. So the upshot of this is that f of r of xz dot, I won't get into this too much, but suffice it to say it ends up having to be r z cross r rx instead of the other way around in order to make sure the orientation is right. But the numbers are the same. I'd rather not get into that quite yet. The important thing is this comes out to being the dot product of x 2 3z dot j dA, which is just going to come out to 2 dA. So the double integral over S5 of f dot ds is 2 times the area of d, once again, which is 2 times 4, which is going to be 8 in this case. And for a similar reason, for y equals negative 1, I'll just skip ahead a little bit. That's 6. Sorry. Backwards oriented, again, this has to be the double integral over over d of, in this case, y is negative 1, so this is x negative 2 3z dotted with negative j dA, and that comes out to 2 times the area of d, which is 8. So it's pretty much the exact same story as before. What we have in this case is, we want to look at the entire surface integral. Again, I made a mistake before, but I'm correcting that now. The integrals of the top and bottom are 12, plus the integrals of the x sides are 4, plus the integrals of the y sides are both 8. So you add everything together and you get a grand total of 48. All right, so questions about how we got this value just by adding up all of the surface integrals from each piece individually. Questions so far? Now the point here is that if you have that your surface is parallel to one of the coordinate planes, which is to say that your surface is of the form z equals c, y equals c, or x equals c, then the normal vector you want, that unit normal, is going to be just one of the usual unit coordinate vectors, I, j, or k, which is going to simplify your calculations enormously. Now, in the next section, we're going to look at some special instances of cubes and things like that, so we'll be able to keep that in mind as well to make our lives a little bit easier even more. So I want us to think a little bit about Green's theorem. Now, Green's theorem tells us that if you take the line integral of a vector field, and that line integral is over a region, that line integral is over a curve that encloses some region, then, well, you can just take the derivatives of the components, qx minus py, and by the way, it turns out that that's kind of like a two-dimensional version of the curl, and that can, not always, but it can greatly simplify your calculations. Now, Stokes' theorem is almost the same thing. In this case, if you've got a closed curve C in three-dimensional space, and you're taking a line integral, a work integral over that curve for some vector field, that's the same thing as taking the flux integral of its curl over the surface that C encloses. And you may be asking yourself, well, wait a minute, what surface that the curve encloses? Because we're working in three-dimensional space. There can be lots of different surfaces that the curve C will enclose. You take, for example, like a, take, for example, let me see if I can do this. A curve where, maybe you're looking at a disk, and you could be looking at the surface that's just the disk itself. So maybe here you have C, and the surface in question, I'll call that S1. But meanwhile, you could have the same curve, the same circle, and maybe the curve in this case is a half sphere over it. And so that's the same C, same boundary curve, but in this case, it's a different surface. What Stokes' theorem tells you is that in both cases, the work done over this boundary is the same in both cases. It doesn't matter which of these two surfaces you use. You can either use the disk, which is perhaps easier, or you can take the double integral over the half sphere. In both of these cases, it'll work the exact same way. That's the beautiful thing about Stokes' theorem, is it doesn't matter what your surface is as long as your boundary is the same way. So that's what Stokes' theorem tells you. So it doesn't matter what surface you choose, both surfaces will work the same way. And by the way, when I say that it doesn't matter what surface it is as long as the boundary is the same, you may be asking yourself, well, wait a second, that sounds awfully similar to what we said about the fundamental theorem for line integrals, doesn't it? And yes, it is very similar to that because it's basically the exact same thing. This is the fundamental theorem of line integrals, but applied to surfaces instead of lines. So, so one of the big takeaways for this section is that we have all of these different parallels to the fundamental theorem of calculus. So for example, we've got the first regular vanilla fundamental theorem of calculus that we saw way back in Calc 1, which tells us that if you take the integral of a derivative, that's the same thing as subtracting off the original value of the function at the start and end points. And that's almost the exact same thing that we saw for the fundamental theorem of line integrals. And that's very similar to Green's theorem, which we looked at before, which is, you're taking a sort of kind of derivative of this vector field. And we said before that turns out that's like the two-dimensional version of the curl. And for the actual curl, if you integrate the actual curl, you get the work integral, and that's just a fundamental, and that's Stokes' theorem. They're all different flavors of the same idea. So everything that we do at the end of the semester is sort of about tying together these different theorems, which are all basically different versions of the same thing. In fact, if you study advanced geometry, they literally call all of these things Stokes' theorem. These are all called Stokes' theorem to some people because they're all basically saying the same exact thing, which I think is really cool. So now just to recall, to remind everybody, the work that's done by a conservative vector field along a closed curve is 0. That's what we said by the fundamental theorem of line integrals, right? If you take a conservative vector field, you're in this second category, and if your curve is closed, well, then that's just the same thing. There's no boundary really. There are no boundary points, so it's one endpoint minus the other, so that's 0. The same principle applies to Stokes' theorem. If you have a surface that does not have a boundary, like a cube or a sphere, if your surface doesn't have a boundary, and you try taking the integral of the curl over that surface, it's gonna be 0. It's guaranteed to be 0 in that case, because there's no curve to integrate over. So the right-hand side of Stokes' theorem just becomes 0 if your surface is closed. That is, if your surface encloses some region. Now, by the way, and we'll see that more when we look at the divergence theorem, which is the final section of the course. But by the way, this has a lot to do also with our test for whether or not a three-dimensional vector field is conservative as well. Now I mentioned before that when you're working with, when you're working with surface integrals, and for that matter, line integrals as well, and you're integrating a vector field, you got to be a little bit careful because because you could have that your surface inherits. You have to be careful with the orientation. So surfaces have orientation and curves have orientation, and Stokes' theorem is only true when the orientation of your surface and the orientation of your curve are in a sense compatible. So what exactly does compatible mean? Well, we'll look at that in more detail going forward, but for now, the image that you should have in your mind is your curve is counterclockwise oriented when you view it from above, if you're working with the graph, which is the most common scenario that we're going to be working with. So for example, you can have your, actually I'm gonna try redrawing that slightly differently. You can have your boundary of your surface. Maybe here's what the actual surface looks like sitting on top of that thing. So the surface is in blue and the boundary curve will be in black. So in this case, if your surface has upward orientation, which most of our surfaces will, we're mostly going to assume that our surfaces are upwards oriented. That means that your boundary curve is going to be counterclockwise oriented when viewed from above. And that's basically what orientation means. The way that I like to describe this is if you have a small individual who's running along the curve, and that small individual is running so that the upward side of the surface is on their left side, which is the scenario in this case. If your surface is upward oriented, then if you ensure that the top is on your left side, that means you're going to be traveling counterclockwise. Now that's what happens when we talk about a positively oriented or compatibly oriented surface and boundary. But we'll look at that in a lot more detail over, as we look at other examples. And that's going to be a major focus of where we start next week. But for now, just think about this as your surface is upward oriented, the curve is counterclockwise, and that leads to this picture. All right, questions so far about anything that we're looking at? Okay, so let's do an example of this. Let's say that we want to calculate the work integral of f dot dr, and f is this vector field xy, yz, xz, and c is the triangle with vertices 1, 0, 0, 0, 2, 0, and 0, 0, 1. Now in this case, it's a good idea to try drawing this because this isn't actually that difficult of a scenario to draw. Drawing it in this case will be quite helpful. So here we have that, I'll do this in pink. Here we have this surface, or the curve rather, 1, 1, 2. Here's our curve. Our curve is, and it's oriented counterclockwise. You're going from 1, 0, so 1, 0, 0 to 0, 2, 0, and from 0, 2, didn't do a very good job of drawing that. Let me try that again. Aha. So, and then you're going from 0, 2, 0 to 0, 0, 1, and then from 0, 0, 1 to 1, 0, 0, blah, 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 blah. So that's our, and this curve is going to be counterclockwise oriented when viewed from above. Now that's the curve we're integrating over. Now, can we integrate over each of those 3 lines individually? Yeah, we can. That might get a little annoying though, and you have to keep track of 3 different parameterizations. One option, a different thing we can do is invoke Stokes' theorem, because you stare at that for a second and it's not terribly difficult to notice, wait a second, that curve is the boundary of this triangular plane. Right? So if this curve is C, then we can say that this plane is S, right? So since we have, oh, sorry. And the important point here is that since S has, and it's this S that we just defined, since S has the curve C as a boundary, we may want to use Stokes' theorem if it's easier. So what I mean by that is if you actually take the curl and it's a better vector field. Because it can happen that you can take the derivative of a vector field and it's a worse and uglier vector field than you had before, in which case, obviously, you don't want to use Stokes' theorem if your curl is making your vector field even worse. But let's see if it is in this case. Let's actually calculate the curl of this vector field. And what do we find? Well, let's go ahead and do it. Del x, del y, del z. Again, doing my OCD thing of saving the ijk for later on to keep space appropriate. Xy, yz, xz. So you take the curl, and what does this come out to? The j term is going to be negative y j. K term is going to be, that's right, I said j, I didn't mean j, I meant I. That was silly of me. The j term, on the other hand, is going to be minus x j. Sorry, not xj, zj. Fix that. And the k term is going to be minus x k. Okay. So that's our curl. Now, given that that's the curl, now that's a nicer vector field than the one that we had before, so maybe we'll want to use that. So what's S? Well, this surface S, so since this is better than F, so we will end up using Stokes' theorem. Stokes' theorem is going to make this much easier than trying to do this directly. We do need to find out what S is, though. We do need to figure out what this surface S is, and this is in some ways the hard part, but it's actually not terrible. Let's see what we can work out for S. So for S, we notice that S is a plane, right? And it's a plane that contains the points 1, 0, 0, 0, 2, 0, and 0, 0, 1. There are a lot of different ways to find out what that plane could be. For example, you can take the cross product of two of those edges, and that will tell you what your normal vector is. And once you know your normal vector, you can plug that in to the usual plane equation. That's one way of doing it. What I'm going to do, though, is I'm going to do something a little bit faster, which is just to say that an equation that all 3 points satisfy is x plus 1/2 y plus z is equal to 1. And just plug in 1, 1, 0, 0, 0, 2, 0, and 0, 0, 1. You see, yeah, that falls out. That immediately falls out. So that makes our lives a little bit nicer. So we can use the fact that S is the graph of the function gxy is 1 minus x minus 1/2 y. And if that's the case, then that's going to give us that Rx cross Ry is going to be, in this case, 1, 1/2, 1, because that's just negative gx, negative gy, 1. But if you look at that vector, you'll stare at that for a second and you realize, oh, of course it's that vector. It has to be that vector. And the reason it has to be that vector is the normal vector for the plane, right? And the normal vector for the plane, we already know what that normal vector is. That normal vector was discovered to be 1, 1/2, 1. 1, 1/2, 1. That's the normal vector that we want. So yeah, it shouldn't be a surprise at all that that's what our normal vector is. So that's good news so far. So we've got a lot of very useful data. We know what the curl is, and we know what our surface is and what our parameterization is. So there's still a couple more bits of data that we need to work out, though. So just to recap so far, what we have is we know what the curl of this vector field is. We calculated that, and we know what Rx cross Ry is for our parameterization. And we're also going to need to know what the curl becomes when we plug in R of xy. That's not hard to work out either. That's going to be negative yi minus 1 minus x minus 1/2 y j minus x k, plugging in what we know to be z in for z. So the curl you dot the curl with Rx cross Ry. What's that going to become? That's just negative y minus 1/2, 1 minus x minus 1/2 y minus x, or in other words, negative y minus 1/2 plus 1/2 x plus 1/4 y minus x, or in other words, 1/2 x minus 3/4 y minus 1/2. One thing we didn't do is we didn't figure out what D is. We didn't figure out what our domain of parameterization. It's the last piece of data that we need to work out. What happens with the domain of parameterization? Well, that D, that region D, I'm going to try drawing it down here, is this region in the xy plane, right? It's this region, this yellow region down here in the xy plane. We need to work out what that is going to be. That's not that hard either because this curve, that curve is just what we get when we set z equal to 0. Or in other words, what we get when we take x plus 1/2 y equals 1, or y equals 2 minus 2x. So now that we can see it that way, we can see that the domain of parameterization is going to be all x and y, so that we have x is between 0 and 1, and y is between 0 and 2 minus 2x. So the curve, so the work integral, we're just about ready to figure this whole thing out at this point. The work integral, f dot dr, is the double integral over your surface S of the curl dot ds, which we now know is the integral from 0 to 1 of the integral from 0 to 2 minus 2x of 1/2 x minus 3/4 y minus 1/2 dy dx. You're left with this iterated integral at this point. In the interest of time, I'm not going to solve out that entire integral right now, but that's because we know how to solve those kinds of integrals from what we did in all the way back in chapter 15.2 specifically. So I'll leave it there for now. But when I upload the notes to Canvas, they'll have the actual answer in them, and you'll be able to compare. But you should make sure that you know how to do this kind of integral. It's not very hard. I'm just not going to do it for the purposes of saving some time. Okay. So now at this point, we've pretty much covered all of the different kinds of integrals that we'll have. So there are two kinds of line integrals that we know. For the scalar line integral, pretty much there's only one way to do these, and that's the direct formula that we looked at in section 16.2. Second kind of line integral, a little bit more sophisticated. It's for vector fields. Now, if your vector field is conservative, then you want to find an anti-gradient, right? This potential function, and use the fundamental theorem of line integrals. If your curve is closed in 2 dimensions, you can use Green's theorem to turn it into a double integral, and that might make it easier. If your curve is closed in 3 dimensions, you can use Stokes' theorem and take a flux integral of a curl. And if neither of those things are true, then your only choice is to do it directly. And one thing I'll point out, by the way, is that, as I said, any surface will do. It doesn't matter what your surface is, as long as it has that curve as a boundary. So you have to choose what your surface is and construct it explicitly. That's the hard part of using Stokes' theorem. That's the tricky part, is actually finding a good surface to use in that case. But if you can, usually there are only a small handful of examples we'll be looking at in this class, but do a lot of examples of Stokes' theorem on your own, more than what's in the homework, because they're tricky, but they are going to, it'll make your life a lot easier if you can actually figure out how to use Stokes' theorem in the right way as you're doing this. But you can go in the opposite direction as well. So what we just looked at was how to use Stokes' theorem when the problem is to calculate a line integral when your curve is closed. But you can go the other way as well, which is to say that you can, excuse me, you can use Stokes' theorem when you're trying to calculate a double integral over a surface, and your integrand is a curl field. So we're not going to get into the divergence theorem and finding anti-curls exactly, but we will say that if you know that your integrand is a curl, then you can automatically just use Stokes' theorem. And you can do that in 2 different ways. You can either just say, okay, well, it's the integral of this curl over the surface, and I can just say that it's here's an easier surface to work with over that curve. So let's do an example of this. What if we have the double integral over S of the curl of f ds, and f, here's your vector field f, and S is the part of z equals 1 minus x squared minus y squared that lies above the xy plane with upward orientation. Now I want to look at what that surface is for a second, because this is very important. That surface, z equals 1 minus x squared minus y squared, that is an upside down elliptic paraboloid. So just to give you an idea, what we're dealing with here. Here's that surface. Right. And that's the surface that we're interested in, and here's its boundary. Its boundary curve is down here, right? This is S. That's the surface we're interested in. But you look at that for a second, and you'll notice, and that's not very well drawn, but you're supposed to assume that that thing is flat on the bottom. But what you'll notice is that actually, that's the exact same boundary as just this S1, which is just the xy plane. So by Stokes' theorem, I'm sorry, you can instead calculate the double integral over a much easier surface, which is just S1. And it's easier because S1 is just parameterized by the function Rxy is x, y, 0 for x squared plus y squared less than or equal to 1. Let's actually calculate this curl and see what we get if we want to do it that way. Well, del x, del y, del z, x squared plus 2y, x, z squared, I, j, k. And what does that become? In the I direction, we get 0. In the j direction, we get 0. In the k direction, we get -1, right? Delta x minus delta y of x squared minus 2y, it's 1 minus 2, so -1. So the whole thing is just negative k. That's the curl. That's a massively easier curl to work with. So that should scream, wait a minute, Stokes' theorem is going to be easier in this case to use over this much simpler surface. So the surface in question is negative k. What about the normal vector? Well, the normal vector in this case for this parameterization, Rx cross Ry, you can see this, is going to be k. And we know that immediately because, well, of course it is. It's just the normal vector that's pointed upward from the surface. So that's not hard to work through at all. So what that implies is that, just to be really explicit here, s, take the integral over the curl dot ds. Well, that would be the integral over the boundary curve, but it's also the double integral over the much simpler surface S1. Which in this case is given by, which in this case we can see that dot product, it's the double integral over your domain D, which is the same thing as S1, in fact, of negative k dotted with k ds, dA rather. Or in other words, negative area of D, or negative pi. We almost didn't have to do any calculus at all. I mean, we had to calculate a curl, but that's the only differentiation that we did. We certainly didn't do any real integration in this case. So this is a much easier problem. Pardon me. This is a much easier problem just by virtue of the fact that our curl was so nice. Our curl was such an easy curl to work with in this case. So so it's very good to become familiar with what happens with Stokes' theorem and being able to use little tricks like this. So we were able to choose a simpler surface and solve this problem. Right. Any final questions before we end? Well, since there are no questions, thank you for those who tuned in, and we will continue our I'll be running the recitation tomorrow, and we'll be looking at more examples of Stokes' theorem and Green's theorem and line integrals and surface integrals, and begin to further develop our toolkit of strategies for how to tackle different kinds of problems and what your thought process should be when you're trying to work through different kinds of integrals. So thank you, everyone, and I will see you guys tomorrow.